So far, we've been looking at overall chemical reactions that look like this and talking about their rates. But it's important to understand that overall chemical reactions don't actually tell us about how a reaction happens. All they tell you is what you put in and what you got out. In this case, we put in a hydrogen and 2 iodine chloride molecules, and we got out 2 hydrochloride molecules and an iodine molecule. So this is like in a recipe where if all it showed you was the ingredients and what you were eventually going to make, but it didn't show you actually how to turn those ingredients into whatever food you wanted to make. So just like we have recipes with steps that tell you exactly what to do with your ingredients, in chemical reactions we can write what's called a mechanism. And this shows how these particular reactants turned into these particular products. So for instance, here's a mechanism for this above overall reaction. First, an H2 and an ICl react to form HI and HCl, and then this molecule reacts with a second ICl to form HCl and I2. Now we can see the overall reaction if we add these steps together. Now we're going to add them up like we do algebraic equations, so things on the same side will add together and things on the opposite sides will cancel. So in this case we have HI on opposite sides, so those are going to cancel. So on this side we have H2, and then now we have, these are on the same side, so 2 ICl molecules. And then again, these are on the same side, so 2 HCl plus 1 I2. So these two steps are called my elementary steps. When we add them up, that's called my overall reaction. And the thing that cancels here is called my intermediate. That should be one word, but I ran out of room. And an intermediate is something that was produced in one step and then used up in another. So we don't end up with any of it, but it was there for a little while. Mechanisms are useful because they do show you how the reaction actually happens. So if you wanted to speed up or slow down a reaction, you could focus on one of these steps and figure out, okay, well, how could I make this reaction go faster, or how could I stop this step from happening? Another thing that's really important is that one of these steps is going to be what's called the slow step. And that's the step that's really going to limit the overall rate of your reaction. Just like if you are on a track team, you're only as fast as your slowest person, my reaction is only as fast as my slowest step. So we can actually figure out the rate of my overall reaction just by looking at which step is slowest. The way we do that is actually just by looking at the elementary step and directly writing the rate law. Since the since the mechanism actually shows which molecules get together, we can directly predict my rate law where the exponents here are directly come from these coefficients. So A and B here turned in my orders there. We can't do that for an overall reaction because overall reactions don't show the steps that are happening. But we can do this for the individual step within a mechanism because then however many molecules you need to get together in that step directly affects your rate. So mechanisms are usually proposed by scientists for a particular reaction, and then you have to figure out if that mechanism is valid, if we think it could really happen. And there are two main things you have to look at. First of all, just making sure it adds up right. That one's easy. And second of all, that the predicted rate law, which is based on this slow step, that rate determining or rate limiting step, matches what people measure during the experiment. So here's what one of these validation questions look like. Consider the following reaction, so this is your overall reaction, with an experimentally determined rate law of rate equals K times NO2 squared. Is the following mechanism valid? So the first thing we do is make sure these add up correctly. So we look for things to cancel out. So here my NO3 molecules are going to cancel out. That would be my intermediate. And then everything else I'm going to add together. Oops, sorry. We have one NO2 molecule cancels out as well. So what we are left with is NO2 plus CO gives me NO plus CO2. And if we go back and check, that's exactly what we expected. So step one, check, they add up to the correct reaction. The second thing we need to look for is, does that rate match the experimental law? So what we do is we look at the slow step and we write a rate expression, rate equals k, a to the x, b to the y, just by looking at this step. Now I know we crossed out this NO2 here because it was an intermediate, but we do have to count it when we do our rate law. So we say, okay, according to the slow step, my rate should be k, and then NO2, and there's no coefficient, so just raise to the power of 1, times NO2 raised to the power of 1. And of course, since those are the same, we can simplify this to be k NO2 squared. And we looked at this step because it's the slow step. So after we write that, just looking at these reactant molecules, we ignore the product molecules, we go back and compare it and say, look, it agrees. The rate k times NO2 squared is what we predicted, and it's also what we got experimentally. So this would be a valid mechanism. That's the kind of problem we're going to do with these. The other thing we can do is relate these to those reaction diagrams we saw previously. So we know we can show reaction diagrams to show if things are endothermic or exothermic, but the other thing that they can be used for is to show how many steps are in a mechanism and which one is the slow step. So every step gives you one hump in your mechanism with its own activation energy, and the slow step is going to have the higher activation energy. Bigger the activation energy, the slower your rate. So for instance, for this one, it's a two-step mechanism. So we always put time here and energy here. It was a two-step mechanism, and the first step was the slow step, so we're going to have one with a really big activation energy, and another one with a smaller activation. Now we always need some extra information. So let's assume this was an exothermic reaction, so that means we're going to end a little lower than we started. So this would be my delta H. If it was an endothermic reaction, then we would have ended higher than we started. So each one has its own activation energy, so that's activation energy 1, and then the second activation energy actually starts from this stopping point right here. So not from the very beginning, but right there instead. Since this one has the bigger activation energy, this one would be my slow step. And I start with reactants, end with products, and here are where I develop intermediates. At the top, we call this an activated complex. So we can sketch an overall reaction diagram as however many steps you have, that's how many humps you have, and the slowest step gets the largest activation energy.